So last time I proved three lemmas. Let me quickly summarize those three lemmas because they're the key to everything. So we had a semi-simple Lie algebra and we were looking at its Cartan decomposition. And let me see, what else had I done? I had fixed some bilinear form, some non-degenerate invariant form. And it may just as well have been the killing form, but I didn't really care. All I'd used so far was that it was a non-degenerate invariant, necessarily symmetric bilinear form. And its restriction down to t is also non-degenerate. And so using that, I'd identified t with t star, so that lambda in t star, I was using the notation just t sub lambda for the corresponding element of t. So that was our setup. And then the first lemma, which maybe I'll write down the first lemma and the second lemma simultaneously. We showed that for a root alpha, C alpha is in R if and only if C is plus or minus 1. Right? So the only scalar multiples of a root are plus or minus the root. The scalar C, of course, could be any complex number here. We'd shown that each root space, each G alpha, is one-dimensional, and we've shown that you can pick E alpha in G alpha and F alpha in G minus alpha and H alpha, which is just defined to be twice T alpha over T alpha T alpha. So this is, of course, in T. So that E alpha, H alpha, F alpha is an SL2 triple in G. So they span the subalgebra, three-dimensional subalgebra, which I'll denote always by G alpha, which is isomorphic to SL2 of C. Okay, so that was lemmas 1 and 2. And lemma 3, so everything was coming, I'll just remind you, from the representation theory of SL2, this fact that we knew that on a finite dimensional representation of SL2, we totally understood what the eigenvalues of H alpha could be. And so this is where all these nice integrality properties that you see in lemma 3 in particular are coming from. So lemma 3 was about alpha and beta being roots, with beta not being plus or minus alpha. But we had let R and Q be maximal. So beta minus R alpha and beta plus Q alpha are also roots. And then lemma 3 told us that all of these guys, beta minus R alpha, beta plus I alpha, all the way up to beta plus Q alpha. So these guys are the entire string. So all minus R less than equal to I less than equal to Q are roots. And I didn't name this thing, but it has a name. It's called the alpha string through beta. So everything in here, this is the sort of the bottom one where you've taken away as many alphas to still be a root, the top one where you've added as many alphas to still be a root, and everything in between for all integers I in that range, all of these guys are roots. And hence, this number, beta minus h alpha, is equal to r minus q, so it's an integer, and beta minus this integer, beta of h alpha alpha, that's one of the guys in that string, so that was a root. Okay, so that was kind of lemma 3, which was the most complicated to state. So I'm going to just add one last little piece of notation down here to this general setup. I'm going to actually transport the form on. So this is our bilinear form on t to t star. I mean, I've identified t and t star, so I'm just going to write lambda mu. It's going to be the same as t lambda t mu, for lambda and mu being in t star. It's just more convenient to work on the space t star, and I'm just going to push the form straight to t star, and I'll always write alpha check for 2 alpha over alpha alpha for alpha in R. Okay, so these are just two little notational things I'm going to add into the game. So I'm going to write alpha check, that's going to be the notation, and I'll call this the co-root corresponding to alpha. So this is something kind of very convenient, this co-root, so you see this quantity here, beta of h alpha. H alpha is just twice t alpha over t alpha t alpha. So beta of h alpha, it's actually just the same thing as beta alpha check in this new notation. Right, so we're identifying, so beta of h alpha, it's the same as just the inner product of beta with the element of t star corresponding to h alpha, and the element of t star corresponding to h alpha is just alpha check in t star. Okay, so in this new notation, these integers, these beta of h alphas that we got in lemma 3, they're just these bilinear forms, beta alpha check, where alpha check is the co-root in t star. Okay, so that's just a summary. It's a long load of stuff, but there it is. There's our summary so far. Definition. A root system is a pair E, R, where E here is a Euclidean space. So I mean a real vector space with a positive definite symmetric bilinear form. And R here is a subset of E of what are going to be called roots. Okay, so that's the data. It's a Euclidean space and a subset of E called R, the roots, and then there are some axioms. Axiom 1, R is finite and spans E. In particular, E is finite dimensional. Property 2, if you have a root, then a multiple of alpha is in R if and only if C is plus or minus 1. The only scalar multiples of a root are plus or minus the root. Property 3, if alpha is in R, then actually maybe I'll write it like this. If you have two roots, if alpha and beta are in R, then S alpha of beta is in R. Okay, there's a little notation there that needs to be explained. So I'll do that over here. I'm going to write S alpha from E to E for the reflection in alpha perp. So little piece of elementary vector calculus, a little bit of geometry and Euclidean space. Maybe you just need to use the projection formula. That's probably what's most familiar to people. There's a formula for this reflection in alpha perp. The reflection applied to lambda, it's lambda minus 2 lambda alpha over alpha alpha alpha. If I didn't have the 2 there, that would be the projection of lambda onto the hyperplane alpha perp. And then with the 2, that kind of moves it out the other side. That's the reflection of lambda in that hyperplane. Okay, so this is, you I'm sure have seen this picture. You know, here's lambda. That's the projection onto alpha perp. And then there's its reflection out the other side. This is the origin. That's axiom 3. So the reflection of a root in the hyperplane orthogonal to some other root, it's again a root. And property 4, if alpha and beta are roots, then twice beta alpha over alpha alpha is an integer. Actually, it's better if I introduce a shorthand when I'm dealing with a root system and write alpha check for 2 alpha over alpha alpha for alpha in R. That's the co-root which I already had on the previous slide. And if I introduce that co-root, well then this quantity right here, this is just beta alpha check. So all the beta alpha checks are integers. And look, the same expression appears here. This coefficient of alpha in the reflection formula, this is just lambda alpha check. So that's kind of a convenient shorthand. Okay, so this is just an axiom definition, just these 4 axioms of root system. Root system is a Euclidean space, a subset of roots such that these 4 axioms hold. R is finite, spans E. If alpha is a root, the only scalar multiples of alpha that are also roots are plus or minus alpha. The roots are closed under reflecting in these hyperplanes orthogonal to other roots. And then this very strong integrality property, all of these quantities beta alpha check are integers. So because what we want to show, the point of writing down these axioms, that R set R of roots coming from the Cartan decomposition of our semisimple Lie algebra is a root system in this axiomatic sense that I've just written down. And you know, we already see lots of this, right? We've already proved this property 2. We've already proved properties 3 and 4. They're both in this lemma 3 that we had, right? We had exactly that. You see these quantities here, these are exactly these beta alpha checks. They're all integers. And we'd shown that if beta was a root, then so was this guy. That's exactly S alpha of beta, according to this formula, because this is beta alpha check. So lemma 3 is exactly checking these axioms 3 and 4. But there's something missing here, because our Lie algebra is a complex Lie algebra. This set R of roots sits inside T star. And so the problem here is that we need a real vector space. We need a Euclidean space, and we've got a complex vector space. So we're really almost there. It's just we've got to construct this Euclidean space E, and actually what we see is this complex vector space T star. So we're close. Let's just do the last little step. So another definition. Given our semisimple Lie algebra G with its Cartan decomposition, I'm going to define E to be, well, I'm going to write this RR. It looks a bit weird. That's the real vector space spanned by the roots in the complex vector space T star. Right, so we've got this subset R of a complex vector space T star, but R spans T star as a complex vector space. And all I'm going to do is I'm going to build this real vector space inside there by just taking the R span of R, the real span of R. And then lemma 4. The dimension of this real vector space E is equal to the dimension of T star as a complex vector space. I think I called this the rank of G before. We don't yet know that it's independent of the choice of the maximal toral subalgebra T, but it will be. This is the rank. So in other words, this is showing that the complex vector space T star is the real vector space with scalars extended from R to C. Or if you prefer it, you could say that E is an R lattice in T star. Okay, that's lemma 4. Let's prove it. So I'm going to pick alpha 1 up to alpha L in R so that they give a basis for T star as a complex vector space. Right, we've shown that the roots span T star, but they're not linearly independent. So let's just pick a subset of the roots that give a basis, alpha 1 through alpha L. So these guys are linearly independent. Over C, hence over R. And of course L, the number of them, that's exactly this rank of G, this dimension of T star as a complex vector space. What we need to do is to show that alpha 1 up to alpha L span E as a real vector space. So we need to take some beta in the root system. Remember, by definition of E is the real vector space spanned by the roots. So all we've got to do is we've got to show that every root can be written as an R linear combination of alpha 1 up to alpha L. Well, we could certainly write beta as Ci alpha I for Ci in C, because these are a C basis. And so what we need to do is we need to actually show that each Ci is actually a real number. Okay, so that's what we're doing. Well, let me just take this equation and take the inner product with alpha j check. So that's the Ci alpha I alpha j checks. Now this guy right here this is an integer. In fact, what we get there is a matrix, which is an integer matrix, because this is each of these quantities that we've shown that those are all in Z. It's invertible. Because alpha 1 up to alpha L and alpha 1 check up to alpha L check are bases for T star. This is not the gram matrix of our bilinear form with respect to one basis, but it's the gram matrix with respect to a pair of bases for T star, and this form is non-degenerate. Okay, so this matrix right here, this L by L matrix, this is the matrix of coefficients appearing in this system of linear equations. It's a matrix that's invertible with integer entries. The inverse matrix, therefore, has rational entries. So I can take this system of equations, J goes from 1 up to L, and I can just solve for the CI's, and because our coefficient matrix, the inverse matrix, has rational entries, and these numbers on the right-hand side, these are all integers, it implies that CI is actually in Q for all I. And that does the job. Okay, I squeezed it in a little bit at the bottom of the slide, but that's the idea. It's just this integrality of this important matrix right here, this matrix of these alpha I, alpha j checks. That matrix is gonna become even more important later on. This invertible matrix with integer entries that we've got kind of emerging out of our semisimple Lie algebra. Great, so now I've got a real vector space, and so now we're very close to proving that our root system R, coming out of our semisimple Lie algebra, we've now sat it inside a real vector space E. So now I'm beginning to have the data ER of a root system, and look, axiom 1 is automatic, right? Our Lie algebra is finite, so certainly R is finite, and we defined E to be the span over the real numbers of the set R of roots. So we've certainly got axiom 1, and we've already checked axioms 2, 3, 4. So we're very, very close. What's missing is the Euclidean space, the inner product on E. So we've still got to construct this real valued positive definite bilinear form on our real vector space E, which we've now constructed. Well, up till now, any invariant non-degenerate form was fine. So I really didn't bother what my form was. I just used this associativity property and non-degeneracy in everything we've proved recently, all of these first 4 lemmas. It could have been the killing form. But I didn't insist on that because I like the trace form better when I'm working with classical Lie algebras. But getting this real valued positive definite inner product, of course, that's a little bit more sensitive to scaling. You can't just scale by any old complex number. You can't even scale by a negative real number because it'll be negative definite, not positive definite. To get the Euclidean space structure, we need to be a bit more careful. It is useful now to look at I think it was homework 6, question 2, all forms are the killing form just scaled by non-zero scalars on each simple component. Most of what we're doing just depends on these quantities, these beta alpha checks, these entries of this matrix that I've just suggested is really what it's all going to be about. And these beta alpha checks, what are they? They're twice beta alpha divided by alpha alpha. These guys actually involve ratios, numerator one form, denominator another form. So these quantities, these don't care when you rescale this form because these are ratios of two inner products. So this scalar really, it hardly appears because most of the theory it involves beta alpha checks, which don't change when you rescale your form. Lemma 5. So I'm now going to finally need to make this assumption that this guy here is the killing form, possibly scaled by some positive real numbers. On each simple component of G. So I realize I'm working kind of hard here to save being able to use the trace form whenever I'm working with a classical Lie algebra. I could have just worked with a killing form always, but there you go. It's not really a big deal to just modify this form a little bit. Then the lemma says that the restriction of this form down to E sitting inside T star is a real valued positive definite symmetric bilinear form making E into a Euclidean space. So that's the final step. That indeed means with this definition of E, so providing we take our form to basically be the killing form, we define E to be the real subspace of T star spanned by the roots, and we just take the restriction of our bilinear form, which we've transported to T star. Then our set of roots, together with this Euclidean space, give us a root system according to those four axioms. Okay, so we've just got to prove lemma 5, then we're done. Again, this is not so bad. What we need to show, we need to show that alpha beta is real for all alpha and beta in the root system, right? Because the Euclidean space E is the R span, the real vector space spanned by the roots. So to show that this restriction of this form down to E is real valued, it just suffices to show that alpha beta is a real number for roots alpha and beta. Oh, and then we need to prove the positive definiteness. We need to show that lambda lambda is greater than 0 for all non-zero lambda in the Euclidean space E. So those are the two things we've got to prove for lemma 5. Well, let's see. Let me just start off by taking any old lambda and me. So actually, I better write one more thing. I'm gonna maybe I write it. No, I can't fit it in there. Okay, so without loss of generality, the form is the killing form. The hypothesis of the lemma basically says that, well, maybe you can scale by some positive real numbers, but that scaling doesn't change the two properties that I'm trying to prove. Okay, so without loss of generality, let's assume it actually is the killing form. So this is the very, very only place in the whole argument that I actually use that this is the killing form. And then I'm going to take two elements, lambda and mu, in T star. And I'm going to compute the inner product lambda mu. So by the way we transported the form to T star from T, it's the inner product T lambda T mu. So it's the trace of add T lambda, add T mu, trace on G. But you see, I've got this Cartan decomposition, and these add T lambda and add T mu's, they act diagonally on the Cartan decomposition. So I can just take the trace, on T itself, T lambda and T mu commute with everything in T. So these adds are just going to be 0 on restriction down to T itself. So actually all I'm going to do is I'm going to have to sum over the remaining part of the Cartan decomposition, all these roots R, alpha in R. Remember, all these G alphas are one-dimensional. And then I've just got to look at the scalar. How does add T mu act on G alpha? Well, it just acts by alpha of T mu. Similarly here, alpha of T lambda, right? So I'm just taking the trace of a diagonal matrix and I'm using the basis coming from this Cartan decomposition. That's that. And let me just rewrite it one more time. By the way, we've identified the form. That's just alpha comma lambda, alpha comma mu. I can push back to T star. So let me call that something. Maybe let me call that formula dagger. So I really had to calculate the trace. That's the one place where I used that I actually had the killing form. Now let's use dagger. So let's take some root beta. So by dagger, this is the sum alpha in R, alpha beta squared. That means that 1 over beta beta is a little bit more convenient. So I'm taking this equation and I'm dividing by beta beta squared to get 1 over it. But that's basically this alpha beta check squared. No, alpha beta check, that's 2 alpha beta over beta beta. So I need to divide by 4. But those quantities we know are integers. So this is certainly a rational number. So this shows that beta beta is a rational number for all beta in R. Therefore, alpha beta, which remember that's, what's the alpha beta? It's basically alpha beta check times beta beta over 2. We know these guys are integers, and we've just shown that those are rationals. So this is a rational number for all alpha and beta in Q. This shows, indeed, that this form is real valued. So we're very close. We've got to finally show the positive definiteness . So by dagger again, lambda lambda, it's this sum of alpha lambda squareds. So it's certainly greater than or equal to 0 because these are all real numbers. If it's 0, well then alpha lambda is 0 for all alpha, but that would imply that lambda is 0 by the non-degeneracy of the form. So actually, lambda lambda is greater than 0, and the form is positive definite. Okay, so that's done all the big work with those 5 lemmas. So we've now shown that you can construct a root system in this axiomatic sense out of the Cartan decomposition of a semisimple Lie algebra. So that's really the main goal of this chapter. But let me give you a glimpse of where we're going to go next. So we've got to think about these root systems in this axiomatic sense. So we're going to talk about the classification of abstract root systems. So this is sort of saying goodbye to Lie algebras for a little bit, and we're just studying this combinatorial structure inside a Euclidean space. And then once we've got that, we'll come back to semisimple Lie algebras. We'll show that any semisimple Lie algebra G is determined up to isomorphism by its root system. In the sense just constructed. So that the difficult part there, which I think I won't give a full proof of, this Cartan decomposition depended on the choice of a maximal toral subalgebra. So that the hard part in step 2 is to show that actually it doesn't matter which maximal toral subalgebras you pick, you end up with the same root system at the end. So that needs something called the conjugacy theorem, proving that all choices of maximal toral subalgebra are conjugate via automorphisms of the Lie algebra G. But so that conclusion of step 2 is that there's a map from semisimple Lie algebras to root systems. We've just constructed the map. It's well defined, independent of the choice of maximal toral subalgebra, and it gives you a way of getting from a semisimple Lie algebra up to isomorphism to a root system up to isomorphism. And that step 2 shows that this map is actually injective. So that knowing the root system, you know the semisimple Lie algebra up to isomorphism. And then the third thing we've got to do is we've got to show that every root system comes from a semisimple Lie algebra. So that this map is onto. And in that way, we'll have completed the classification of semisimple Lie algebras. It'll reduce to the classification of root systems, and that's going to be our topic of the next chapter. In fact, we'll show that just as semisimple Lie algebras are direct sums of simple Lie algebras, root systems are sums of indecomposable root systems. And the indecomposable root systems are going to be classified by what are going to be called their Cartan matrices. You can write down a Cartan matrix for any root system. The indecomposable ones are the ones that can't be broken down into block diagonal matrices. And those indecomposable Cartan matrices are going to be just turned into diagrams, called Dinkin diagrams, which you've probably seen. So Cartan matrices are going to be important. And we've actually kind of already almost seen them. Those are these matrices, these alpha I, alpha j check matrices. But for a slightly more careful choice than we made above. Of the basis alpha 1 up to alpha L. So it's that matrix, that invertible integer matrix, which you've already seen a bunch of times was important in those 5 lemmas. So in that way, we're gonna get from a root system, we're gonna get this Cartan matrix. And then we're going to find that the indecomposable Cartan matrices are labeled by Dinkin diagrams. So let me just at least draw the Dinkin diagrams. So they're all labeled by the rank which is the dimension of that Euclidean space that the root system sits in. So that AL, BL, CL, DL, E6, E7, E8, F4, G2, and let me see if I can draw them. So the L is the number of vertices in the Dinkin diagram. BL is similar, it's just a string, but for B you have a double bond at the end. C is similar, you have a double bond at the end but with the arrow the other way. D is similar, but at the end you have a branch. E6, E7, E8, and then F4, and G2 actually has a triple bond. So those diagrams are going to label the root systems. We've kind of already seen AL. This is going to come from the Lie algebra SLN of C, where n is L plus 1. Remember, L is the dimension of the maximal toral subalgebra, which in SLN is the traceless diagonal matrices. So L is n minus 1, the dimension of that. And in this case, actually, we've already seen the Cartan matrix. I didn't quite have all of this fancy notation in but I showed you this matrix appearing by looking at the gram matrix of, I was using the trace form at the time, on our maximal toral subalgebra T of SLN, and I showed you that particular basis, H1 through Hn minus 1. And in fact, this will turn out to exactly be the Cartan matrix. So we'll work through this in a little bit, but you see this Cartan matrix is basically this Dinkin diagram. I mean, you can sort of almost put this on top. Let me do that again. You can almost put that Dinkin diagram on top of that Cartan matrix, down the diagonal there. Those 2's down the diagonal, they're the nodes, and those minus 1's above the diagonal or below the diagonal, they tell you the edges. That's kind of how you get Dinkin diagrams out of Cartan matrices. These double or triple bonds come when you don't have just minus 1's above the diagonal, but you have maybe minus 2's or minus 3's. And you'll see how that goes. So that's all in store. In the next chapter, though, I've got to spend a little bit of time just talking about the general theory of root systems in Euclidean space, and then we'll be ready to go back to semisimple Lie algebras.